So this is the lecture 3 which finally happened. And I thought that I spoke about masses. Now I should talk about the mixing, but it's very complicated. It's not very complicated, but it's very vast. That's why I said a flavor of, and I hope you will understand why. Now, I will tell you about little bit of references because these are 2 recent reviews which really helped me. This lecture was supposed to be given by Professor Ketan Patel, who is my colleague in PRL. He is really an expert on this field and I am really not an expert in this field. But I found these 2 reviews which really helped me. So I would like to advise you that you can go through these reviews, and then there are all the references you will find there. These are few references which I have used for preparing this. Now, the way I have done this is the following, that it's you will realize when I talk that it's really a vast field and a lot of research has been done on these topics. When in 95, I was a PhD student, I read a review by Professor Paul Langakar, and in that he wrote that the models of neutrino mass, the papers on the models of neutrino mass can be a candidate for the dark matter. So, that's the thing, that's in 95. So you can imagine how the field has flourished now. But it's very interesting. I hope I will be able to give you the flavor of that. Now, you have seen the fermion mass spectrum from many people, so I don't dwell on this, but I want to highlight few points. One is that neutrino masses are much less than quark and charged leptons, which you have already seen. Now, there is also an interesting thing, which is the hierarchy of neutrino masses not strong. If I take M1 as 0 and I take delta M squared 3,1 and delta M squared 2,1 values, then this is less than 6. And when we consider inverted hierarchy or quasi-degeneracy, there are no analog of that in the quark sector. So what's going on differently in the neutrino? Then the thing is the flavor puzzle. So you can see that these are the sort of the size of the CKM matrix, and this is the size of the PMNS matrix. If I write the mixing angle, in the quark sector, all the mixing angles are small. In the neutrino sector, there are some, still it's not settled, but these are the kind of best fit values. So this is the very different. So the thing is that the neutrino flavor mixing as well as the neutrino mass spectrum, these are very, very different from the quarks as well as the charged leptons. Why that is important is because, when we go to grand unified theory, we try to unify quarks and leptons. And if the quarks and leptons are very different, then, we have to put some special efforts. Like the simple way, it may not work. Now, I will come to this. We have seen that a Dirac mass term is written between a left and a right-handed state. So, if I add a right-handed neutrino in the standard model, I can write a Dirac mass term. But since I have 3 flavors of neutrinos, E mu tau, then in general, this is a 3 cross 3 matrix. And when I am assuming that I am adding the right-handed counterparts of this, so what we have is a mass matrix. This is a Dirac mass matrix where this Le, L mu, L tau are not conserved. I have done this, I think, that the Majorana mass matrix can be written as this, psi L bar, psi L C. I have shown that. And here I am showing, I think I showed it earlier also, that the Majorana mass matrix is symmetric. Did I show it earlier, right? That the Majorana mass matrix is symmetric. You can use the properties of C. So here what one does is one first does expresses nu LC as C nu L bar transpose. Then you take a whole transpose because it's a scalar, so you can take a transpose. When you send a fermion field this side, you pick up a minus sign. Then you use the property of the charge conjugation and we get that mm equal to mm transpose. And if you have a symmetric matrix, then this can be diagonalized by a unitary matrix U transpose MMU. Now, one thing I forgot to mention here, which is that the Dirac mass matrix is in general, it can be complex and it can be, non-Hermitian. So sometimes what one does is, if one takes MD dagger MD and then one can diagonalize it, but with a unitary transformation, or one can use a biunitary transformation. So what you can do is, this is a good thing for you to check, that if I have a symmetric matrix, then it can be diagonalized by this. So you can use a biunitary transformation. There is a discussion in the Cheng and Lee, the book, that how you do the diagonalization using a biunitary transformation. And from that you can show as a corollary that if your mass matrix is symmetric, then it can be diagonalized by U transpose U or U star U dagger. Okay, so that is a thing we have to remember. Second thing is that we have, now the second thing which I wanted to tell you that, we did the seesaw. I told you how this MD transpose comes, but when we did the seesaw diagonalization, we took MD square by MR. We took MD as number. One thing which you should learn is that if this is a matrix, then how do you get this formula? This derivation you should do. So the way it is done is, one of the way is that first you bring this to a block diagonal form. This is a Majorana matrix, so you can use this to bring it to an off diagonal form. And you, in this approximation that MR much greater than MD, which is my seesaw approximation, this U can be written as this form, MD star MR inverse and MR inverse MD transpose, and the block diagonal matrix is MD MR inverse MD transpose. So this is my mass matrix in the Flavour basis at low energy for the light neutrinos, and I diagonalize this with the UPMNS matrix to get my neutrino mass matrix in the diagonalize, and this is the right-handed mass matrix. This is the seesaw approximation, MR much greater than MD. If I take ML to be not equal to 0, then I get a ML here. This is the type 2. And this derivation that, how do you do this seesaw diagonalization? It's actually a paper. It is a paper by Grimas and Lavora in 2000. And if you are working on these things, then then it will be really good for you to do this. Because, if you do this, then it will really help you to do the other diagonalization, like, if you are using inverse seesaw or linear seesaw, or if you have some model, then you can follow this and you can do the diagonalization. So this is my M nu in the Flavour basis, the mass matrix for the light neutrino. The UPMNS matrix diagonalizes this to give me the mass eigenvalues. Here, since I know the solar mass square difference and the atmospheric mass square difference, only one remains unknown. The other two can be expressed in terms of the mass square differences and the lightest mass. So depending on whether you have normal hierarchy or inverted hierarchy, either your M1 or M3 is lightest. This is the mass matrix for the light neutrinos. This MEE is what you probe in the neutrino-less double beta decay experiment. So for the light neutrino mass matrix, only this element you can probe directly for the from neutrino-less double beta decay. But since you know the U and you know these masses, so you can invert this equation and you can express all these in terms of the mass eigenvalues and the mixing angles. Now we talked about the UPMNS. Like when I spoke about the UPMNS, then I had assumed that the charged lepton mass matrix is diagonal. So actually the origin of the neutrino mixing you can understand if you write the charge current interaction. So this is in the Flavour basis, where you see that I have the nu alpha and L bar alpha, the Flavour states coupling with the W. Now if I go to the mass basis for the charged leptons as well as for the neutrino, when I say that, between the mass basis and the Flavour basis of the charged leptons, this matrix stays. And between the neutrino mass and Flavour, this U nu, this should be U nu stays, then my UPMNS becomes UL dagger U nu. And if you assume charge lepton matrix as diagonal, then UL is 1, and then my U nu is the UPMNS matrix. So then how do we parameterize U? So if I have a n cross n complex matrix, then I have in general 2n square parameters. If I apply unitarity, I will get n square independent elements. So of which, I have n C2 angles, right? And I have this many phases. So this is a calculation everyone should do once in their life. But some interesting things from here, that if I supposing take n as 2, then I will have 2 into 2 minus 1 by 2. So I will have one angle and I have 3 phases in general. But if I am in the Dirac case, then 2n minus 1 phases can be absorbed. So if n is 2, 3 phases can be absorbed. That's why in the Dirac case, my neutrino mixing matrix will not have any phase. Yesterday Poonam mentioned, she also mentioned that if it is Majorana, then we can have a phase. So we should see why in the Majorana and the Dirac, the number of phases are different. So like I said that supposing I have 3 cross 3, then I have 3 into 3 plus 1 by 2, 6 phases in general, right? So the Majorana mass term is like this. So this is nu and this is nu transpose, right? This is not invariant under the phase transformation we have seen for the lepton number, right? So then supposing, so the way we absorb the phases is that we absorb them in the neutrino and the L. So when I say 2n minus 1, then I absorb in the the charged leptons. I redefine my charged lepton state, I redefine my neutrino states and I absorb. But here I cannot do it. So the phases of the mixing matrix, if absorbed here, then in the neutrino field, they will reappear in the mass matrix. So this is also, you should do it yourself once and see. So then, only three phases can be absorbed for the 3 generation. If I have 6, then only 3 phases can be absorbed and I will have 3 phases remaining. This is for the 3 generation. So I may be going little fast because I want to come to flavor mixing. But the thing is that these are the pointers and I would like you all to do these calculations for yourself and convince yourself that what I am telling is correct and you should once do it. So then this is my matrix. This you have many times seen, R23, R13, R12. I have the delta, and if I have the Majorana case, then I will have an additional phase matrix. Okay, so I have 2 Majorana phases, 1 Dirac phase for 3 generation. And these are the values from the NewFit collaboration. So the thing is that, okay, so I want you to do one exercise now so that there is some kind of an involvement. So if you put theta 1, 3 as 0 and theta 2, 3 as 45 degree, what is the matrix you get? I will wait for 2 minutes and have water so that you just calculate. Theta 1, 3, 0, the form is given in the last line. Theta 1, 3, 0 and don't take the Majorana phases. Just take theta 1, 3, 0 and theta 2, 3, 45. So if I put theta 1, 3, 0, theta 2, 3, pi by 4, then I get this matrix, right? So the theta 1, 2 is not known here, okay? There are various cases which are discussed in the literature. One is the bimaximal mixing for which theta 1, 2 is 45. Another is the tribimaximal mixing for which the sin theta 1, 2 is 1 by root 3. Then there are golden ratio, hexagonal mixing, etc. So what we will consider in this lecture is tribimaximal mixing. So what I am trying is, okay, first let me say that, this is then what are the different approaches that exist when we try to explain the flavor mixing. So one is the anarchy, where one does a random analysis without any bias on the known neutrino mixing and masses, and one sees what prediction one gets. One is the bottom-up approach, where we find out the patterns of masses and mixing low scale from data, and we try to figure out what is the symmetry at the high scale. And another is the symmetry approach, where explicit symmetries are assumed at the Yukawa-Lagrangian level. And these can come from flavor or horizontal symmetries, gut, or combination of both. There are also now these modular symmetries. So this is the symmetry approach. So this is the thing that so horizontal means we know, like from the standard model, we know that this nu E or SU2 like that. So when we are saying horizontal or family symmetry, we are saying that this nu E, nu mu, nu tau, they are belonging to some multiplet of some group, okay? So similarly, one does also for the charged leptons, and gut is like vertical. So in grand unified theories, what we do is we put the charged lepton, the neutrinos and the quarks in a same multiplet depending on which group we are using. SO10 is a good group where you can put, it has a 16-dimensional fundamental representation. So you can put 6 quarks including their color, the 6 plus 6, 12, and the neutrino and the electron and the right-handed neutrino in the same multiplet. So that makes it 16. So then what happens is that, we can automatically explain neutrino mass in SO10. So SO10 is a very popular model. We can implement the seesaw for the neutrino mass. So that is the gut, and this is the family symmetry. So what I will do is I will give you an example, and I will try to give you the bigger picture with respect to the example. So this is a matrix which most of you have got. Now what I will do is I will use this U, so this is the U0, to diagonalize this. If I use this U, then I get a matrix of this form. Okay, so this is a very simple mathematical program which I have written to just check when I was preparing this talk. So you can just do a simple mathematical program to check. Now this X and Y are what? They are in terms of, expressed in terms of the M's and the angles, right? The mixing matrix. So these are big expressions, so in this page I didn't write. The important thing to notice is that this M has a symmetry that M nu equal to A23 M nu A23, where A23 is like a 2-3 exchange symmetry. So this matrix has a symmetry where nu e goes to nu e, nu mu goes to nu tau goes to nu mu. So if you do this exchange, then you can do it in two ways. You can do this multiplication, or you can change the row and the column, and you will see that you will find the 2-3 row and column, you will find the same matrix. Okay, so this is called the mu tau permutation symmetry. Now this matrix gives, if you write this matrix in terms of this U0 and this M's, you will find an expression for sine square 2 theta 1 2 in terms of these parameters. Okay, and like there is no prediction, but you can put some conditions to get, like I have shown you that if x plus y is equal to w plus z, then you get sine square 2 theta 1 to 8 by 9, or you get the tri-bimaximal mixing angle. It is a homework problem for you to check how you get the bimaximal mixing problem from this. Bimaximal mixing means theta 1 2 is 45. So this is a homework problem for you to check how this gives me the bimaximal mixing. Okay, I have shown you how it gives you the tri-bimaximal mixing. Now you can, diagonalize this, find the eigenvalues. You can see that, under what conditions you get normal hierarchy, under what conditions you get inverted hierarchy. So these are certain conditions which you can get, and both are possible. This kind of structure does not give us any prediction for the Majorana phases. So this you have to do little bit of exercise with this matrix and see. Like I have not included the Majorana phase here because theta 1 3 is 0. I need not include the Dirac CP phase. I could have included the Majorana phase by multiplying this by a phase matrix or multiplying this by a phase, and I could have done the whole exercise using the Majorana phases. Then this would have been in terms of some complex parameters, but we will see that there are no predictions for the Majorana phases that you can see. So this is the form. I was telling you that you can write this in terms of, when I write UTBM, then I write this mixing matrix now, because my sine square 2 theta 1 to 8 by 9. So my theta 1 2 is this 35 degree. I think it should be 3. So then this is the tri-bimaximal form, and then you can write your M mu tri-bimaximal in this way. Now what we want to understand is, what we want to identify is the sum of the symmetries under which this matrix remains invariant. And what we can find is that there are these symmetries, like which is this G3 TBM, this given by this matrix, G2 TBM and G1 TBM. Under these three matrices, this M nu remains invariant. And what are these? You can see that if I take identity and G2 TBM, this forms a Z2. Then G3 TBM also forms a Z2. This G1 TBM also forms a Z2, 1 and G1, but these are not, three are not independent. And the thing is that each is responsible for one column of U. So I need two independent to get two column. The third will be fixed from the unitarity. And also these are the generators of S4. We can also see, what we have done here, the charge lepton matrix as diagonal here. I have not taken any form of this. Then you can see that this will be invariant under this T, which is a generator of Z3. Now I talk about 3 discrete groups. One is Z2, one is Z3, one is S4. Are there people who do not know about these groups, or who knows about these groups? Okay, so not many hands. Anyway, like as I said, that when I do particle physics, there is a lot of group theory involved. So it will be good for you to do this. I will show the multiplication table of Z2 and Z3. S4 is the group of permutation of 4 objects, and it has 24 elements. So when we do the group like S4, then in group we always have 1. Then we have like this 2 cycles, that 1, 2, 3, 4, like that it will go. Then I will have where this means like 1 goes to 2, 2 goes to 1. So I change. So if I have 1, 2, 3, 4, then I will change 1, 2. Here this means I will change 3, 4. So my element will be 2, 1, 3, 4 here, like that. So I can also have 1, 2, 3, 4 where I change both at a time. I can have 1, 2, 3 where I change 3, and I can have 1, 2, 3, 4 when I change 4. I should have had 5. 1, 2, 3, 4, 5. Yeah. So I have 5 types of 1, 2, 3, 4. 5 types of permutations of the group S4. So you should do this, and you can see that you have 24 elements. So the thing is that I followed a bottom-up approach. I started from tribimaximal mixing. I identified the mass matrix. I identified the symmetries of the mass matrix, and the symmetries of the mass matrix took us to 3 groups, Z2, Z3, and S4. So that is the thing that this is the example I wanted to give to show you. Now I can start from the opposite way. Supposing I start from S4, then I have to identify the generators of S4. So discrete groups also have generators, and by that we mean that these are the elements in terms of which you can express all other elements. So all 24 elements of S4 can be expressed in terms of these 3 elements, S, T, and U. And I can take a 3-dimensional representation. So, then we have to consider the representations of S4. And the for representation, what you should know is what are the conjugacy classes of S4. And okay, this is not always true, but for S4, I can say I have 5 conjugacy classes corresponding to 5 different types of elements that we have. Okay, so I have this 1 cycle, I have 2 cycle, I have 1, 2, 3 change, I have this 4. So I have 5 conjugacy classes. And what are the dimensionalities of then if I have 5 conjugacy classes, I will have 5 irreducible representations. And the dimensionalities of the representations should be such that x1 square plus x2 square plus x3 square plus x4 square plus x5 square is equal to 24. So because these are sum of squares and I know 1 is 1, you can solve this, and we know that this is 1 plus 1 plus 2 square plus 3 square plus 3 square. So I hope I am right, 18, 22, 23, 24. So from this I know, so if I know the properties of S4, I know its conjugacy classes, then I know how many irreducible representations it has, and I know their dimension. So we have 2 3-dimensional, 1 2-dimensional, and 2 1-dimensional representation of S4. Okay. So we are interested in 3-dimensional representations because we have 3 flavors, right? So, but this is a general scheme. It's not that I didn't write the Lagrangian. You have to write a Yukawa invariant Lagrangian, and then you may need other representations also for the scalar fields. So you can identify this as G2, this as T, and this as G3. And we have seen this, that T ML dagger T is this, and S transpose M nu S is S, and S and U makes M nu invariant, and T and T dagger makes ML dagger ML invariant, so they commute, and then what happens is this gives us the tribimaximal mixing. So I showed you in 2 ways. One is that I considered the bottom-up approach, I considered the tri-bimaximal mixing matrix, I considered the mass matrix, I showed the symmetries of the mass matrix, and these are the generators of S4. So then S4 is a good group for explaining tri-bimaximal mixing. So this is the scheme, S4. So I saw that T generated Z3. So S4 is breaking to Z3, S4 is breaking to Z2 cross Z2, and then combined we are getting the tri-bimaximal mixing. So why this is called the method of the residual symmetries. So we have a group at a high scale, then we say that this is broken to different groups in charged leptons and neutrinos, which makes a lot of sense because charged leptons and neutrinos have different kind of properties. So that's why we are breaking it to 2. And I considered an example where the charged lepton mass matrix is diagonal. So this was UL was 1, but you can also consider something else. And I have these 2 Z2s which will fix my tri-bimaximal mixing for the neutrinos. And this is the multiplication table of Z3. So I wrote the generators. You can check that they satisfy this multiplication table, and this is the multiplication table of Z2. So you can see that they are satisfying the multiplication table. So up to this, what I have done, if you go through my notes and if you do yourself the calculations, it will become much clear to you. I also learned it here, like doing the whole calculation. When these few days I got, I did that, and I find it very interesting. So I will ask you that, this is like real fun. So you can just do it and see how things fall into place. So the residual symmetry approach is that, find a group GF and identify the generators. Identify the generators for the subgroups GL and G nu, and GF is broken to GL and G nu, and this gives rise to fields known as flavons. So I am not going into the detail of any model, but I am just showing you that this is the thing, that GF breaks to GL, G nu. If I have a non-trivial UL, then my U is UL dagger U nu. And this symmetry breaking is through scalar field called flavons. So if I try to be a little more mathematical, then what I will say is that, I have a matter field in some irreducible representation of GF, and they will transform according to some unitary irreducible representation matrix in the Rth representation. And this is the transformation or the generator under which ML dagger ML is invariant. So when my lepton fields transform under this representation and the neutrino field transforms under this representation, if we take the neutrinos as Dirac, then I have to take this M nu dagger M nu as I have mentioned. And then I have these transformations. So, when I get these transformation generators under which this M nu and ML dagger ML are invariant, then diagonalizing those generators will give me the U's. So that is the main thing. I have shown earlier that the generators were commuting with this. So that is not surprising. And there is, I think, a theorem also which says. So the thing is that we identify the generators under which these matrices remain invariant, and diagonalizing those generators will give us the mixing matrices. So this is the example which we have considered, and I have given you the general approach. Now you can ask me is that, I started with tri-bimaximal mixing. I had theta 130, so I don't know anything about delta Cp. And you have seen in the earlier lectures that theta 13 has been measured, it's non-zero. Delta Cp is also probably non-zero, most likely. So how do you generate that? Again, I will take an example. Earlier, I had considered a mu tau symmetry. I will here, that is called a mu tau permutation symmetry. Here I will call something which is known in the literature as mu tau reflection symmetry. So what does that mean? In the mu tau permutation symmetry, I said nu e goes to nu e, nu mu goes to nu tau goes to nu mu. Here I am saying that they go to their charge conjugate states, nu mu and nu tau and nu e. So this is mu tau exchange plus there is a Cp transformation involved. And this is the matrix under which they transform. And if I take the mass matrix for this, then invariance for the mass, this is my S, then S transpose M0S should be M star. And if I put this S and if I put this M0, then I can find my U0 and I can see that this is the form of my U0 now. And if I diagonalize this through the U0, then I will get diagonal plus minus mi, right? So then the Majorana phases are like plus minus. So they are 1i, so the angles are 0 or pi by 2. So this mu tau reflection symmetry gives us some predictions for the Majorana phases, although they are like the trivial. So this is like the plus and minus. These are called like the 0 or pi by 2. So they are giving the Majorana phases like this. And I can write this a matrix with the U nu as the Majorana phases. So in the earlier case, I didn't get any prediction for the Majorana phases. First, I have got a prediction for the Majorana phases. And let us see what we get for the mixing angles. So if I take this mixing angle matrix, then you see here my mod u mu I equal to mod u tau I. And this gives me theta 2 3 pi by 4 and S1 3 cos delta Cp 0. So this is also, you can do this exercise. These are just 3 cross 3 simple matrices. You can use Mathematica. I did by hand this part, and then you can get this. So everyone should check. These are really simple checks. So then I have this option, S13 cos delta Cp 0 means I can have theta 13 0 or I can have delta plus minus pi by 2. These models became very popular because, at one point of time we thought from the data that delta is close to minus pi by 2. So this mu tau reflection symmetric model becomes popular. So what is the general principle then we can infer from this? The general principle that we can infer from this is that I had the mu tau exchange symmetry, with that I put a Cp symmetry, okay? So that is what is the general principle behind this. Now you should ask me that, your theta 2 3 is pi by 4. So not pi by 4. So how we are getting this? So there are some models which can do it, which is that relaxing mu tau reflection symmetry. For the third column, we don't put it. We just put it for the first column and the second column. And then I can get some relation between theta 2 3 and delta. This can again come from some models, but because this is again a different model, so I didn't want to go into it. What I am trying to tell you is that, what we do is we start from a symmetric limit, theta 2 3 0, theta 2 3 pi by 4, theta 1 3 0. From that symmetric limit, we go to try to generate the non-zero theta 1 3, non-zero delta Cp. Then we try to relax this, and this is not the only way. In the backup slides, I have another way where you can generate this kind of thing. So there can be many ways in which you can generate this. You have to take your favorite model and try to see if it works. And when I have this kind of correlations, then these correlations can be tested with the data. And so, this is from an older paper of ours where we have plotted the sine square theta 2 3 delta Cp correlation using these C1 and C2 conditions, and these red areas were the allowed region in sine square theta 2 3 delta Cp around 2018, and this blue is the prediction. So you can see that when we have these Flavour models, then we can have some predictions, and they can sort of, along with the some allowed parameter space, they can disfavor. So this particular model allows this part, and it disfavors lot of this part, the model prediction. And this part the model allows, but the data doesn't allow. So these are the kind of things, Sanjay was mentioning that if you have the data, then what are the kind of things one can do? And one can also test that this kind of theta 2 3 delta Cp correlation, can they be tested in some future experiments? So there was one point of time which is like this 18, 19, 17, that time these kind of papers became very popular, that you take your model and you try to see that what is the prediction for the data, and what is the prediction for the mixing, and if there is any correlation, then whether the future experiments can test these correlations. Now if the model is also giving some prediction for the Majorana phases, then you know the kind of neutrino-less double beta decay plots you have seen, where the funnel region is due to certain values of Majorana phases, then you can know that whether those regions are getting allowed or not. So these are the kind of lot of work that people did around, means they are still doing. So these are the kind of things you can do with this in the data. So then this example brings me to something called the generalized CP invariance. So the action of a generalized CP transformation on a field operator is to put this as minus x, and this is an unitary operator, x dagger as 1. Okay. Now the requirement of CP invariance tells us that x transpose m nu x is m nu star, and x star ml dagger ml x is ml dagger ml star. Okay. Now the point is this, that supposing we have this experience, only this symmetry, can we generate the phases? And the answer is no. If we have only a generalized CP invariance applicable on the mass matrices or the fields, then all the phases come out as 0. So this is a big proof. This is, you know, the reference will be there in the reviews that I have written. And it is instructive to do this because I thought it is very interesting, and it motivates us that why we have to take a Flavour group and a CP group even for generating non-zero CP phases. Of course, the angles we won't be able to generate with this, but even for the CP phases, we need a Flavour group, right? So we had a mu tau exchange symmetry and a CP. So the thing is, we consider the case with both Flavour and CP symmetry, then we get predictions for CP phases and mixing angles. So this is an example which I had given, that you know we had this extra CP symmetry. So then, I started with S4 when I did exchange symmetry, but what I have here is S4 cross CP. Then in the charged leptons, we had this broken to Z3, but in the neutrino sector, now it will break to a Z2 cross CP. And then I will have, you know, 1 omega nu, so 1 Z2 will determine 1 mixing angle, and I will have a general matrix, and I will have this Majorana matrix. This is a general principle thing. Like, this is not the only way. This is the example which I have given, from which I am showing you. There can be different ways of generating these things. I considered the, you know, S4, the non-abelian Flavour symmetry group S4, which has 24 elements. But these are a few examples where you can have these three-dimensional representations. There are many, many groups which one can show, and you know, like A4 is actually a subgroup of S4. A4 group is considered a lot, and you can see that A4 has these generators S and T. S4 has 1 U, so S4 is a bigger group, and here I have this S and T. Okay, so one can consider different groups people have considered, and one can do these things. Now, I discussed the method of the residual symmetry approach and the generalized CP approach. There are various approaches. One is called like sum rules. Sometimes people say, okay, there are some sum rules, like, you know, one point of time it was very popular, quark-lepton complementarity, that you have the quark angle plus the lepton angle equal to the Cabibbo angle, something like that. And then you see that whether they are stable against renormalization group running. Then the charged lepton can give us a correction. Sometimes, you know, we can do that. Okay, you have tri-bimaximal mixing, whether the charged lepton corrections can give us theta 1, 3 non-zero, and can depart from theta 2, 3. Then there are something called texture zeros, which are that, you know, when we have the low energy mass matrix, then we can show that from the data, the maximum number of zeros you can have that matrix is 2. And from there you can get some predictions. You can consider 1-0 textures also. Then there are something called modular symmetries, which avoids the flavons. So that is also very popular now. So I'm just giving you a snapshot of all that. And by the way, this is taken from this paper. And what these people did in this paper was took all these kind of different models, and they studied what happened to neutrino-less double beta decay. So that was their aim, to see that, the implications of all the Flavour models for neutrinoless double beta decay. And I did not discuss the grand unified theories also. You can have E6 also, that comes from SO10. If you consider inverse seesaw models, then E6 is a good group to consider. Then you have also SU5. SU5 does not have a neutrino naturally, the normal SU5, but if you consider a 24-dimensional representation of SU5, then the type 3 seesaw can be implemented. In SO10, we can implement the type 1 and type 3 seesaw. And this is the left-right symmetric model, where also we can implement the type 1 and type 2 seesaw. And all these groups, there can be some way of symmetry breaking using different scalar fields, but finally they should give us the standard model. That is the basis of the grand unified theories. Okay. Now the thing is that what kind of things we can do now, supposing we have so many different models. So one of the options is to test, different models. This is from a 2016 work, but there are these kind of works done earlier also, and I think later also. That you see, you have this green is the Flavour model, okay, and you have predictions for delta Cp. Now you can see that Flavour models are very difficult because they have whole range of prediction of delta Cp. But then we have GATT models, and this is like, we had some 24 models. There can be more models also. But for instance, if I have these models with anarchy, then they are giving delta Cp as plus 90, close to this. But if I know my delta Cp is here, then I can say that, okay, the models with anarchy may be ruled out. But the Flavour is very difficult because, you can modify your model in so many different ways to give lots of predictions. So the thing is that what one has to do has to take a comprehensive approach, and you can consider the predictions of the models for various things like neutrinoless double beta decay, and many other things. People do the Flavour models in the context of leptogenesis and other things. And if you can get a comprehensive, parameter space, that is the kind of thing one can do. So, okay, I think that I have finished what I wanted to say, and I can take some questions, and I have some backup slides which I can also show if you are interested. Like I showed you one way of non-zero theta 1, 3 and delta Cp, but I can have S4 going to different Z3 and Z2. This is Z3, 1t t square, not different, but I can go this to Z1, Z2, and then I can generate, TBM times the theta 2, 3 and phase. So this is the another way of doing this through the S4 model, and you can have different types of predictions for, different mixing angles, JCP, delta Cp, and also there are multiple ways, so that makes the field very rich. But there are a lot of options, and here I just have some of the subgroups of S4. So I considered Z2 and Z3 and like C2 and C3. So they are like subgroups of S4. We have many subgroups of S4, like A4 is also a subgroup of S4 which people have considered. And these are the kind of dimensions which they have. So we have these three-dimensional representations of S4 which we have considered, and A4 also has some representation, so then people also consider A4. So I think that I can take some questions because I could finish early. And yes, you should.
2-3 questions. So you showed this. First, we consider a mass matrix and consider some, let's say, tri-bi-maximal mixing, and then identify the symmetries. So, is there any systematic way to identify those symmetries, or is it just hit and trial from the mass matrix?
There is a systematic way, because if you go a little deeper into it, then you can see that this Z2, like that's like a charged lepton would have a U1 symmetry, because if you do a phase e to the I phi, then that will remain invariant. So that is, there are some ways to identify that. Like people who work on this, when I was doing it, I was also finding it little arbitrary, but people who work on this, I don't find it so arbitrary, because there are ways that that there is a Z2 symmetry in the like 2Z2s, like 3Z2s in general. So it's not so arbitrary when you are dealing with it.
Okay, and one more. So the flavon, the scalar field that breaks the S4,
Yeah,
S4
or
group into
any
Z,
symmetry, yeah.
So are what are the constraints on the flavon mass? What is the mass scale of that
See,
flavon?
that will depend on the model, usually heavy. But then you can write different types of terms, like you take the flavon fields in some representations of that group. One can write higher dimensional operators also, including the flavons. Usually we take, Rahul, you want to make any comment? Or Rukmini? Yeah. Question was that are there any constraints on the flavon fields?
The mass ranges kind of.
Heavy, yeah, that is the thing.
So, like in general, there is no, you can go model by model, and then in a given model, there might be some constraints.
But usually they are taken as heavy, right, Rukmini?
Yeah, typically you take them heavy, and if you take them super heavy, then there is nothing, no constraint at all. But in certain models, if you try to make them light, then you can put constraints.
Actually, flavons have many problems. You write this model, Lagrangian, then you have to minimize the potential. So if you are considering certain flavor solutions to give you your mixing matrices, etc., then you have to show that proper minimization is occurring. And in order to avoid many of the problems related to flavon, people have gone to modular symmetries.
Yeah, first of all, it's a scalar. That's
Yeah.
But last question. So this S4 cross CP that you were talking about, so there you were considering the CP is a good symmetry and it's spontaneously broken at some scale, and then is it like that? Or?
CPI didn't break, at least in this example, because I had a Z2 cross CP. So it went to one Z2 and one CP. So what they say is that first example I showed for tri-bimaximal mixing, it was broken to Z2 cross Z2. But sometimes they are breaking to Z2 cross CP. But there are some models also when there are spontaneous CP violation through the waves, there also people can generate
like the
CP violation. Yeah, those kind of models are also there. I didn't, go into the details of a model because then that will take a full lecture. So what one has to do is people do this S4 or A4, these are easy. Then what you should do is you should write down the full Lagrangian and then work out. There are some very initial papers of A4 by Ernest Ma and Professor Rajashekaran. So these are the first A4 papers. So you can take them and you can work out one model, and that will raise many questions, and that will tell you many points which I could not cover because I just wanted to give you the general principle within one lecture.
Ma'am, in slide 34, you said we can implement type 1 and type 3 seesaw in SO10. So
SO10, I said type 1 and type 2.
Type 2 you said.
Type 3 in SU5.
Okay.
People have also done, here you can choose representations. In fact, I now remember I have worked on one model where I did some type 3 in SO10, but then you have to choose a proper representation. But normally the canonical SO10 is type 1 seesaw. And then, if you go through left-right symmetry breaking, then left-right symmetry needs a triplet Higgs. So left-right symmetric model gives you a type 2 seesaw. So then that you can embed in SO10.
Ma'am, in that next or maybe 36 slide where you have shown that number of models versus delta CP. Yeah, I think 35.
Yeah.
Yeah, so here I can see that only the anarchy. So there only one point is like 60, only I think delta CP has the value of 70 or something.
Yeah.
So is it like that if the experimental proof of the delta CP value is 70, then only this model will be applicable and all the other models will be
No,
totally
see,
discarded?
if it is 70, then you have the green, you have these all models available. Only so the thing is that the flavor models, you can do many magic with the flavor models. But the anarchy may be little bit restricted. Andre is one of the person who worked on anarchy initially. I think it has some restrictive thing, but I don't know, now if they have found some way to have anarchy prediction here, I don't know. But when we did it in 2016, that time the anarchy models were giving E70. But so if you have delta Cp as minus 120, then you won't have anarchy. That you can say. And I don't know if this area is empty, maybe we didn't find models which are here. We have only a small set.
So this range like minus 120 to minus 180, there is like no predicted model is till now.
I think among the correct reply will be among the models which we considered. But I am sure there will be some models you can fit something to have the prediction here. That's what I think.
I have very naive question. So simply these flavor symmetry we use to describe mostly the mixing angles and CP. So is there somewhat way where we can build model like to distinguish inverted ordering or normal ordering?
Sorry, I have not talked about this, but in all these models, you can diagonalize the mass matrix and you can see that what kind of hierarchy you get. As far as my knowledge goes, this kind of models can give both, but there are, models like LE minus, L mu minus, L tau symmetry that will give only inverted hierarchy, not normal hierarchy. So there are certain models which will give inverted hierarchy, but not normal hierarchy. But I think these flavor models that I considered, so a complete model should do that also. First of all, from seesaw model, we know that the masses are small, but here we are assuming, okay, some kind of thing is taking place and we know the small masses, but you have to work that out. So you have your mass matrix, you do the diagonalization. So for instance, the first model that I considered, the papers say that you can get both kind of hierarchies, normal and inverted. So all you have to do is you have to just diagonalize this, and you have this XYZ in terms of m's, and you have to see. So each model should check that also, that whether it is getting normal hierarchy, inverted hierarchy, proper mass square difference. So finally what you have to do is you have to really do a fit with the data. And then you take all the constraints, the cosmological mass, sum of the masses, everything, and then you see if a model survives or not. That is true for all models. You have to fit all the available data. Okay. But I didn't talk about any detail of any model because there are so many. So I just talked about the residual symmetry approach of generating flavor mixing. But you should do it. At least for these two cases that I did, these are really easy cases. So it will be a good exercise for you to do this, and you can take help from these papers that I have shown here. There it is very well described. All these that I have said are very well described in these review articles that I have said. So I encourage you to do these calculations. You can write very simple Mathematica programs, and I have those programs also. And I have all the calculations done. I didn't know much about it. I just learned it here. So I have done all the calculations. So if you have any doubt, you can ask me also.
In this mu2 symmetric model, we have considered the maximum theta through triangle. So
first version, second version also, yeah.
Yeah, so I don't know whether is it possible that we can, introduce some kind of symmetry breaking parameter and get slightly deviation from these maximal values.
There are various ways of getting that. I just described one way of partial mu tau symmetry, but I also described another way in the backup slides that you have from S4, you have a different symmetry group breaking generators and you can generate. So the TM1 and TM2 mixing, those calculations if you do, then that is one example of what you are asking, which I did in the backup slide. I thought I may not be able to cover, so I put it in the backup, and I also did not want to give too many examples because the basic premise should be very clear, and then we can really work out the model. See here, this model, where I have these things generated, this can have a non-zero theta 2, 3. Departure from pi by 4 here. So, yeah. These models, you can fit, this U23 is a theta, and then you can fit your data and you can see that what is theta.
Will it depend on the particular symmetry group we are considering?
It
Or
will,
is
I
it
think,
like independent of
in
model?
every symmetry group, there are ways to, I started with the mute-out reflection symmetry. There may be some group which is not giving to start with theta 2, 3, pi by 4. So there are many options, many groups. So, but usually it's easy to start with a symmetric limit and then develop from there.
Okay, so let me just ask the last one small question. So all of this depends on the parameterization also. I mean, what parameterization one is trying to use to begin with. But in general, a 3x3 mixing matrix we can write in different forms. And if we choose different parameterizations, the predictions for a given model would be different.
See, the parameterization is like the what you are measuring from the experiment. So at the end of the day, we are trying to connect with the experimental data. So one has to fix a
So like when we say-
parameterization. If you are talking about the parameterization of the mixing matrix. So now supposing my theta 1, 2 is not theta 1, 2, then I will have a mapping. Also, like I think it was discussed in Sanjeev's class that this parameterization happens to be the most economical parameterization given my solar and atmospheric
true.
mass square difference.
That is true.
Because, you know, if I have this R23, R13 and R12, and I had done some paper earlier, 95, when this LSND data came to show that your smallest mass square difference. So, you know, this 1, 2, if you draw here, then I have 2, 1, 3. So 1, 2 is sort of degenerate we can take with respect to 3. So this 1, 2 rotation if you give here, then you know there are certain situations where these will not come in your picture. You take a different parameterization, Sanjeev also said, you do your calculation, you will see that your, supposing you do the PEE calculation for Diabe, it will come in a complicated form. So it is really good that, you know, because CKM also we follow this, and my neutrino mass square differences are such that, you know, this CKM type of parameterization works. But
That is true,
so,
yes. But the predictions of the model depend on the parameterization chosen.
yeah,
That one
but
can
that
safely
will,
say.
that is making the connection with the data.
Sure.
Now, if I take a different parameterization, then I will get a different, but then we have to make
Then
a
our interpretation
mapping with
of
the
different
data.
angles would become
Yeah.
different. That is true.
Yeah.
In the mute-out reflection symmetry model, you talk, it gives some hint of Majorana phases. Could you please explain?
Yeah, so the Majorana phases actually are coming because, you know, I am showing you, you diagonalize this matrix. Just do this diagonalization and you are getting this plus minus mi. So, you know, you can take the Majorana phase with the u, I have shown first, but you can also take the Majorana phase with the masses, because my mass eigenvalues should be positive, right? That is my thing. So I can adjust the, if they are negative, then I say that the Majorana phase is pi or pi by 2. So I have cos pi e to the I pi by 2, that is cos pi by 2 plus I sin pi by 2. So my Majorana phase is I. If I have a cos pi, then I can say cos pi plus I sin pi. So then that cos pi will give me minus 1. So do the diagonalization and then you can see. So this is the like plus minus 1. I can have many combinations with the 3 things.
Okay. So I presume there are no more questions. So let's thank Professor Goswami for this very nice talk.